Hey everyone, my name is Josh. I'm a third-year engineering student at the University of McMaster, and today I'm going to be going over a review video of the Chemical Engineering 2E04 class, Numerical Modeling and Solutions. This video is going to go over everything covered that is going to be in midterm 2 of this course as of my year, 2023 fall term. We're going to be going over several concepts and then hopping over to MATLAB to code them. The concepts we're going to be going over are regular falsy method, multiple open methods for solving solutions of nonlinear equations, along with regression, both of linear regression and basis functions. Without further ado, let's get into things. We're going to start out by talking about the regular falsy method. The regular falsy method is a bracketing method used to find the solution of a nonlinear equation. What this does is it creates a line between 2 points that are bracketed between a x whose y is above 0 and an x whose y is below 0. From there, it makes a line between the two of them and updates the solution as such. It repeats this until it finally converges at a specific solution. So if we have something that looks like this, what the regular falsy method does is it picks 2 points, 1 point being at what I'm going to call XU. This is the notation I'm going to use today. And 1 point at what I'm going to call XL. Now, XU covers the upper bound, which is when f of XU is greater than 0. And XL covers the lower bound, where f of XL is always going to be less than 0. XU means X upper, XL means X low. Let me show you what it does. So we draw this what's called a secant line between the 2 points. Wherever the point finds a solution at the 0 points, at the x is equal to, or at the f of x is equal to 0, we make this a new point. In this case, it's going to be our new XU, XU1. From there, we'll do the same thing. We'll draw our line. We'll go to where f of x is equal to 0 on that line. We make this our new XU. And we keep drawing this line until finally, as you can see, we've come to converge on a solution. And that's kind of just due to my pen being weird, but as you can see, I've kind of converged to where the true solution is. Now let's derive this expression and convince ourselves that our equation for it's going to make sense. So we're creating a line. As we know, a line is y is equal to mx plus b. In this case, our slope is going to be kind of from this distance here and our y-axis. So this is going to be our total y. And this here is going to be our total x. We're making the slope that models the hypotenuse of that triangle there that I just made. And the equation to the slope is going to be rise over run. How much did we go up versus how much we went horizontally, just like in grade 9. So we do f of xu, which is how high we are, minus f of xl, x2 or y2 minus y1. We're then going to divide that by x2, which is xu, minus x1, which is xl. The trick to this is you can have this equation, or as long as you flip both the numerator and the denominator, that works too. It would be f of xl minus f of xu divided by xl minus xu. In this case, I like putting my xu's as my 2's and my xl's as my 1's. Now, we know that our y is equal to mx plus b. If we were to plug in a specific point where we know both the x and the y, we can find our b. I'm going to plug in xu. I like using that for this derivation. So f of xu is going to be equal to my slope multiplied by xu plus some b. Now, what is our b going to be? Well, our b is just f of xu minus xu multiplied by our slope. B is equal to that. Now that does look confusing, but bear with me, trust me on this one. It works out to look pretty simple. So now that we have our m and our b, we're going to keep those there. We're going to have those be constants. We're now going to dive right into our regular falsy method. We say that when y is equal to 0, our x is equal to our new xu or new xl. In this case, we're going to call this when f of x is equal to 0, our x is going to be equal to x r. That's just the notation that I'm used to. So let's write that how it would look like in the line segment notation. 0, because our y is 0, is equal to m multiplied by xr plus b. Now, we would find xr, our new solution, by rearranging and solving for xr. We would do this by taking b minus m, not b minus m, minus b divided by m is equal to xr. Now, let's write that out in full. So our b is going to be here. I'm going to toss xr on the left side. And it's going to be negative b. So we have negative f of xu plus xu in that big blob divided by our slope. So I'm just going to multiply it by 1 divided by our slope. Or, you know what, I'll just take the inverse of our slope. See that? The inverse of our slope. If this is our slope here, I just kind of flip the numerator and the denominator. From here, let's look at what we can do. Now, I want you to notice I put these big red brackets around what was our b term, because it's getting multiplied by the inverse of m. So I just didn't want to get confused there. Now, look at this little trick we can do. Well, what I can first do is I can cancel out, actually, my slope that's kind of attached to my xu term. But I do have to multiply the inverse of my slope in these blue brackets here. I have to multiply that into the negative f term. They cancel when I multiply it by the xu term, but obviously it doesn't when I bring it into the other part of this equation here. So now, this gives us our finalized equation for xr. Our xr is going to be equal to xu. I kind of just brought this in front. Minus f of xu multiplied by this big equation here. And that, everyone, is the finalized regular falsy equation. Now, that begs the question, what do I do with my xr once I found it? Well, I know it's going to turn into either xl or xu. How do I know which one it turns into? Well, that has to do with some if statements that we're going to put into our code. And I'm going to write them out explicitly here. If, when we plug in xr into our equation, so f of xr multiplied by f of xl, if that value there is greater than 0, then my xl term becomes my xr term, because we know f of xl that is a negative value. If it's multiplied by another negative value, then it's going to be greater than 0. The only way where I can get my f of xr to be a negative value is if it's somewhere in here. And we know from a regular falsy method that it would have to be at some point that is closer to my real solution. So I'll update my XL and replace it with what I just found. But on the other hand, if f of xr times f of xl is less than 0, well, then that must mean I have to change xu. And that's going to be equal to xr, which is what was going on in this diagram up here. My new, I'll use a different color. My new f of xr is closer to the actual solution than previous. And then if I multiply this point by this point, well, I'm going to get a negative sign. So I'm going to replace xu. If on the off chance we get f of xr times f of xl is equal to 0, well, then we're super lucky and xr is our true solution, which that would be pretty lucky if we got that. Now, there are a few points or a few situations where our regular falsy can fail, actually. So these are our failure scenarios. Our first failure scenario is if the root to our equation is actually on an f of x is equal to 0 term. In other words, the derivative at the true value of my solution is equal to 0. An example would be on a parabola that's like centered at the x-axis, like right here. This will be my solution because that's when my parabola is in contact with the x-axis. Its x is, or the f of x is equal to 0. But I can't bracket it, can I? Right? What's down here? Nothing. I can't bracket it. Another failure scenario is if our roots is outside what we've labeled to be XL and XU. This is usually if we're just taking a random stab at finding the solution to a function. Normally bracketing methods, we have to see the function first and then have a good guess about what XL and what XU should be. Other than that, that's all the regular falsy method that we're going to be going over. Now let's hop into MATLAB and whip up a simple code of it. All right, so here we got a code of the regular falsy method up in MATLAB. I'm going to show you guys how it works, and hopefully you can try it with yourself, maybe with a function or two. I know in the class that we're in, we have a few problems where we're given some functions to try out with the following methods that we're about to use. So try it out and let's see if you get the correct answers. So looking at the regular falsy method, very simple. It goes just as how we were doing it in those notes back there. I'm just going to quickly pull up our notes on my screen. So what we have is we have a function. It's going to output the XR, which is the X at the root that we're able to converge on. It's going to spit out also the number of iterations that we're looping in. And finally, this is the name of the function, as well with the X lower initial guess, X upper initial guess, and F being the function that we're calling. Just a side note, if you're calling this function, you're going to have to call it as so. So it will be regula falsi. You're going to put in your XL, you're going to put in your XU. And then when you call the function, you're going to have to do at, and then whatever the function's name is. Okay? So going in here, stepping into the code, we've got a tolerance. So this is going to be the stopping criteria. It's going to be able to tell the code when we want it to stop iterating. We have our initial guess, I guess you can say, for XR. This is just so we can plug it into our function to begin with and test the tolerance. And we've got the iteration counter. So I like to do this using a while loop. You can do this using a for loop as well. There's one part of the code that I'm just going to add in when we get to it. Check if you can see if you can notice what I'm missing. So this while loops makes our code stop at the tolerance value. So while the absolute value of f at xr is greater than or equal to our tolerance. So the reason I'm doing this is because we know we want to find the root of the equation. So our equation is going to stop iterating once we have the absolute value of f of xr equal to around 0. Our tolerance is very low. It's close to 0 because we want our root. Next, we step into the loop. Every time it iterates, it's going to up the counter by 1. We do our numerator, which is the xu minus xl term, the denominator, which is our y terms, f of xu minus f of xl. And then we have our root finding, which is going to be xu minus f of xu multiplied by the numerator divided by the denominator. From here, we do our if checks. So if of f of xr times f of xl is greater than 0, we said that means our answer is closer to the real root, but it's a negative value. So we're going to make that our new XL. Else if, so we want to check another if statement. This is just for consistencies here. Else if f of xr times f of xl is less than 0, this means our root is closer to our true root, but it's above the x-axis. So we're going to replace xu with xr. And else, this means f of xr times f of xl is equal to 0, which means we found the root, therefore we break, and it's going to give us our xr value. Now, the one piece of code that I forgot to add in is our stopping criteria. So we should also add in a variable at the top called maxes. This is our maximum amount of iterations. Let's say 1,000. I'm then going to add another if statement that says if our code exceeds our maximum amount of iterations, we're going to break and we're going to spit out what our value is. So if it is greater than or equal to max it, break. Beautiful. Semicolon there. And that's it. That's the full regular falsy code. Okay, now we're going to be going over rate of convergence. A rate of convergence is a very simple thing to think of. How fast is my code going to find the solution? Depending on what method you're using, you might take a small amount of time to find a solution, or it could take a long time. So rate of convergence is going to show how fast code converges. And more specifically in the number of iterations it takes to converge. Now we're gonna do some more notation. We're gonna say RA is the rates of improvements. Each iteration, how much closer do I get to my real solution? Am I taking big steps to my solution, or am I just taking little tiny steps? That's the rate of improvements. We're going to say I is our iteration number, and RC is our convergence rates. So our rate of convergence is going to be equal to our rate of convergence, sorry, our rate of improvement is equal to our rate of convergence to the power of I, to the power of the number of iterations. So for bracketing methods, my rate of convergence is always going to be 1, which means the more iterations I do, does our rate of improvement go up? No. If our rate of convergence is 1, then our rate of improvement is always going to be 1. And we'll see how our rate of convergence changes while we get to our next topic, open methods. Open methods are generally more common than bracketing methods because they have a faster rate of convergence. So they improve much quicker. The first open method we're going to work on is very similar to our regular falsy method. This one's called the secant method. The secant method, it requires 2 points in order to work. These points are going to be what I'm going to call xi and xi minus 1. So what those are is it's our current xi as well as our older xi. And those xi's is our most recent solution that we found and our previous most recent solution that we found. And I want you to see if you can find any parallels between regular falsy and the secant method. Xi plus 1, which is going to be our updated solution, is going to be equal to xi, our most recent solution, minus our function evaluated at our most recent solution, multiplied by this specific slope. Xi minus xi minus 1 divided by f at xi minus f xi minus 1. There you go. That is the equation we're going to be using for the secant method, and it can be easily implemented into MATLAB by just following our regular falsy code and plugging in this new equation instead. And of course, our stopping criteria is going to be if the absolute value of f at xi plus 1 is less than or equal to our tolerance. Now, what is the difference between my regular falsy and my secant method? Well, our regular falsy method relies on our function being bracketed between a negative function value and a positive function value. But our secant method actually, it doesn't rely on that. We have a value or a function that kind of looks like that. If we call this xi, and then this xi minus 1, we draw a line between the two of those. We find, that's a really good yes, we find where the solution to that line is, or the roots of that. And then we call this our new x. Now, I'm looking at this and I'm kind of regretting drawing it because I'm going to get a poor guess for my next one, where I'm going to draw a line from now my older xi. I'm going to draw it through here and look at where my solution is. I actually don't have, it's kind of not in my function, right? But if I were to do some better initial guesses, I might get some more lines that'll lead me to go all the way here. or alternatively here, right? So let's pretend, I don't know, maybe our first line, instead of bringing us there, let's draw a better one. Maybe something like this. We'll try this. Our line brought us here. Now, oopsies. Now, since here was my solution, that's my new XR. And then I'll draw another line between then my oldest point and there. But then look what happens. Uh-oh. I got to go all the way up here. And now I'm drawing a line between these two. Oops. It can get a little sloppy, but eventually it's going to converge. And what's cool about this one is its conversion rate is actually faster than regular falsy. It's equal to the golden ratio, which is 1.618. So it'll converge much faster than the regular falsy method. Now, obviously, it's going to fail if we have a kind of two y values that look like this. So if we're looking at that equation, if between my 2 points, they have the same y value, then we're going to fail because it's not moving. And then we're going to get our x's divided by a big fat 0. And that's not good, obviously. So that's one failure scenario. So a failure scenario, f of xi minus f xi minus 1 is equal to 0. It can also fail if we oscillate between a max and a min. So if we have something that looks like this, oops, that's not very good. We might get a solution that kind of has us oscillating here between a max and a min. And we're never really going to converge on a true solution. Now let's go into MATLAB and let's code that one up. All right, now here up here is the code for the secant method. As you can see, it mocks the regular falsy method, but we don't need those if statements anymore because we're on an open method. We're not bracketed, so we don't need to change XL or XU. So let's go over what this is doing. Our function is, again, is going to give us xi is our new name for the root. You'll see why I did that in a second. The number of iterations. Our secant, we have to insert two initial guesses again. The first one being xi and our second one being xm minus 1. So that's kind of like our oldest guess kind of thing, if you remember what we're doing in secant. And then obviously f, just remembering when we call f, it has to be the at symbol. Same tolerance as before. You'll see this pretty much standard as all tolerances. Iteration starts at 0, maximum amount of iterations at 1,000, while the absolute value of f of xi, that is our root value, is greater than or equal to our tolerance. We step into the loop. We put our iterations up by 1. Remember, so now our xi is our XU, and our XM minus 1 is our XL, kind of mocking the regular falsy method. Our X is at the top, our Y's are at the bottom, and obviously we're matching up the XI's with the XI's, and the XM minus 1s with the M minus 1s. Then what I do here is I put XR equal to some value. So XR is our intermediate variable that we're going to need to use in order to change our variable names. So I put XR equal to the secant method there, XI minus S of XI times the top over the bottom. From there, I make my XM minus 1 variable equal to the current XI. Notice how I'm not iterating or I'm not updating that value beforehand. And then I make my XI variable equal to that placeholder XR. And then I have my if statements for my maximum amount of iterations, along with that break, and then the end statements. Just to show you, if I were to do this instead and make XI equal to our secant method, updating it straight away, I'm going to comment this out. What's going to happen if I run this code is you can see I'm currently updating my XI. So if I try to then update my XM minus 1 to be equal to XI, it's not going to work because I don't have that intermediate value. And if I put XI, what would I add that to, right? So this intermediate step of having it named to be XR is very important. It's very important because it allows us to rename our variables and it allows us to update our variables in order to maintain that accuracy. All right, that's it for the secant method. Now let's move on to the Newton-Raphson method. Okay, now let's take a quick pause and look at what's called the Taylor series. Now, the Taylor series are really important in computers, actually. They are what computers use to model functions and to find really complex numbers. So recall what a Taylor series is. Given value f of x, where we know x and y being f of x, we know what f of x is, we can find the value of f of x plus delta x through a Taylor series centered at x. What's delta x, you might be asking yourself? That's just the step size. So given a graph, let's say we have a function that, I don't like that function. Let's say we have a function that kind of looks like this. I'm just doing the same thing. Whatever. If this is my x value, our step might be this width. So then this value is x plus delta x. What is our step? So if we draw out f x plus delta x, if we ever say x centered at any number, the centered at is just telling you what x is going to be. So x centered at pi just looks like this. Or x centered at 2 would look like that. Not awful. So now, f of x plus delta x, what's that going to be equal to? Our Taylor series expansion looks like so. F of x plus f prime of x multiplied by delta x. That is our first order Taylor series because my delta x has a value power of 1. So I can say delta x to the power of 1. And if we want to get really technical, this f of x term here is getting multiplied by x delta x to the power of 0, which we know is just 1. Let's do our second order Taylor series, which is going to be the same thing as what we have, but we're going to put our second order derivative multiplied by delta x. What's the exponent going to be? Well, it's second order, so it's squared divided by 2 factorial. And just for fun, we'll do our third order Taylor series, delta x cubed this time, divided by 3 factorial. And if I'm being really technical, we could say divided by 1 factorial here. So that is our third order Taylor series. And remember, our Taylor series is an infinite series. So this can go an infinite amount of times. And what's really cool is that f of x plus delta x, the exact value of this solution is equal to the infinite order Taylor series. So if we stretch this Taylor series out infinite amount of times, we're going to get the exact value down to the decimal place of our function. And that's what computers do. They kind of take that function, they plug it into a Taylor series because it's a polynomial and it's super easy to compute. It stretches it out a bunch of times, and then it gives you that exact value. What's important, though, is to remember that our Taylor series has diminishing returns. Meaning the more values I add to it, the less those orders are going to contribute to my true solution. So more values, less each new value adds. So what we can say is that our second order Taylor series added more value to our end product than if I plug that third one in. Same thing. That first value there added more value to my end product than both of these. And that works that infinite amount of times. Now remember, when we do our Taylor series, it fits an nth order polynomial to our graph. So let's say if we had kind of like a sine curve going on. Maybe we had something like that going on there. Our first order polynomial would just fit, and this is our x maybe. Actually, I can do one better for you. If this is x, and then that there is x plus delta x. If I'm to fit a first order polynomial, what is that? That's a line. I can fit, totally, I can fit a line to that graph. And you know what? That fit too well. And you'll see why in a second. Cool. We'll do that. X plus delta x. So that's our first order Taylor series. What's our second order Taylor series going to look like? Well, what's a second order polynomial? It's just a parabola, right? Second order, I can fit a parabola to it. And hey, look, that fit pretty well. You know what would fit even better though? A third order polynomial. Something that maybe looks like that. Ah, that looks even cooler. So the more parts that we add, yes, the better our approximation is going to be. But again, what's the difference between the purple line and the blue line? Not that much, right? Not that much at all. And something that I think is good to add is how can we improve our Taylor polynomial? There's two ways. Way number one is obviously add more terms. Number two is to decrease delta x. Remember what I did at the very beginning there? When I drew that line, my delta x was small. And then I drew that line and it was a pretty good approximation. But then when I made that x plus delta x value further away, so I increased delta x even more, and that line approximation wasn't as good. So if I'm to make delta x super duper small, we can say that our first order Taylor polynomial would probably perfectly fit. So I'll show you that again. So this here is x, and then I made this value here, x plus delta x. Let's draw a tangent, or let's draw our line. Look at that. First order Taylor series, boom, we got it. I'd say that's pretty on the money. And one more thing to add on to our Taylor series polynomial, before we kind of dive into a little bit deeper into it, is that an nth order f of x an nth order f of x polynomial is perfectly fit by an nth order Taylor series. So if we have a fourth order polynomial, a fourth order Taylor series is going to be exactly that polynomial. Now we're going to look at something called the truncation error. And this is very important in the realm of computer and math, because truncation errors is how you get those slight errors from using different methods. So we know if we do let's say we'll do a first order Taylor series polynomial. So we said that looks like this, equal to f of x plus f prime of x times delta x, right? Is that our full Taylor series? Well, no, we said our Taylor series goes on an infinite amount of times. We could add f double prime delta x squared. Boom, we could add this one too. Boom, we could also add this one too. Just like that. But do we need it? No. We're doing our first order polynomial. Why would we add all this for nothing? I just said it's diminishing returns, so let's just get rid of this. Well, we need to remember that these values, along with all the values that go on to infinity, are technically still within this polynomial. We call these our remainders. And the order of our remainder is going to be whatever order the smallest term is in the remainder. In this case, our first order Taylor polynomial here has a second order remainder. So the remainder is of order 2. If we were to make a second order Taylor polynomial, our remainder would be of order 3. Now, we actually have a good guesstimate of what our remainder can be. And it's modeled with this equation. R of n plus 1, which is the remainder that we have for an nth order polynomial, is equal to f to the n plus 1th derivative multiplied by some number that's just some random number. So the n plus 1th order derivative evaluated at some number multiplied by delta x to the n plus 1 divided by n plus 1 factorial. That is exactly a remainder term. And what's cool about that number that we just kind of defined is that this value is bounded by x and x plus delta x. Our derivative is always going to be evaluated between those 2 points because we're trying to find a value at x plus delta x. So why would we evaluate a derivative at something outside of that? It makes no sense. So this is pretty cool because we can find an upper bound to our remainder. We can find the maximum value our remainder is going to be. We can find the biggest value of that. So we can say that the n plus 1 remainder is always going to be less to or equal to f with the n plus 1th derivative evaluated at x plus delta x multiplied by delta x, to the n plus 1 divided by n plus 1 factorial. That is the absolute biggest a remainder can be. And all this knowledge about Taylor series is going to stick with you if you decide to, do some more within computer science, because it's used for this next method we're going to use. It's used for numerical integration, numerical differentiation. It's used for all of that stuff. So it's very important. Now for the final open method, we're going to be talking about the Newton-Raphson. The Newton-Raphson method. Now this one's pretty cool. This one's my favorite method that we're going to be going over in terms of roots and solutions, because it's really easy. It's based off a Taylor polynomial, and it's relatively short. So we're going to say, for this one, we're going to use a first order Taylor polynomial. And assuming we use this first order Taylor polynomial, where delta x is very, very small. It's really small. So x plus delta x, that's pretty much just x. Okay? And we assume f of x plus delta x, which in this case is pretty much f of x, is equal to 0. This means x plus delta x, so the x we have plus that really, really small value, is equal to our roots. Now, let's write out the first order Taylor series of that. So our first order Taylor series is pretty much equal to 0 because we said f of x plus delta x is equal to 0, which we said is also our Taylor series. So that's equal to 0. That is equal to, well, we just wrote it out, f of x plus f prime of x multiplied by delta x. Now let's solve for delta x. Delta x is equal to negative f of x divided by f prime of x. From there, after we find what delta x is, we can find a new guess, an iterative guess of our solution by saying xi plus 1, our next iteration, the solution, is going to be our current solution plus delta x. Now, the more iterations we do, the smaller our delta x is going to get until we converge finally onto a solution. And if you don't like that notation, well, if we do univariate Newton-Raphson, then we can just go right to this. Xi plus 1 is equal to xi minus f of x divided by f prime of x. And obviously, it's going to fail if f prime is equal to 0, or if it's near a minimum. Fail f prime 0 or near minimum. I'll show you a diagram of what this thing here is doing. So we have this first value, and we're going to draw a tangent line. Boom, right here. This is our new solution. Let's walk up to our point, and let's draw another tangent line. All right, that'll be our new solution. Let's do one more, and when you look at that, we found the true solution. Pretty cool. That's why I like this one. It's really quick, and it converges really fast. All right, now let's move on to multivariate Newton-Raphson, which isn't that much different, okay? So multivariates. And multivariate Newton-Raphson. So if we were to draw a first order Taylor series, for this F1, which has, let's say, 3, is that there? X1, X2, X3, 3 variables. Now, the cool thing about multivariate Newton-Raphson is it's going to find a solution for a system of nonlinear equations. These nonlinear equations are going to, obviously, it's going to be square. So if we have 3 variables, well, we're going to have 3 functions if we want to find a unique solution. So how will we write a first order Taylor series for this, this function here? Well, we have to have a delta x for each variable. So x1 plus delta x1, and also x2 plus delta x2. And then obviously x3 plus delta x3. How would we write this? Well, we know first and foremost, we have to write our f1 value evaluated at x1, x2, and x3. But from there, remembering the first order Taylor series has a derivative multiplied by delta x. If we want to do this for 3 variables, we have to do 3 different derivatives multiplied by 3 different delta x's. So we would do the derivative with respect to x1, delta x1, plus the derivative, with respect to x2, delta x2, plus the derivative of x3 times delta x3. And if we were then to use the fundamental of the Newton-Raphson method, make the left side equal to 0, and keep the right side, well, by rearranging, you would get negative x1, x2, and x3 is equal to all of these derivatives. Now, as I mentioned before, if we have three variables, then we also must have three equations, three f's. So altogether, we would have a derivative of f1, x1, the derivative of f2, x2, and then the derivative of f3 with respect to x3. Then we would go down to the next row, and we would do the same with our next function, the derivative x2, and so on. And we would do this all the way up until we get the derivative of f1 with respect to xn for n order, or our n amount of variables, and then the derivative of fn, n being the final function with respect to xn. In our case, it would be f3, x3. Then we would get delta x1 all the way through to delta xn, equaling our negative functions, negative f1 all the way through negative fn. And that is that equation there, or that sequence. Now our stopping criteria is going to be a little bit different. We're only going to stop if our f, the magnitude of our f matrix, xi plus 1, is less than our tolerance. Now, just like before, our new x's, xi plus 1, is going to be equal to xi plus delta x. And everything in these two matrices are evaluated x at the current evaluation. Then we're going to solve this system of linear or the system of nonlinear equations. We're going to solve it by solving for our delta x's and then updating our values. Let's open a MATLAB and then see how that works. All right, so as promised, here's the code for the Newton-Raphson method. We're also going to kind of go over the multivariate Newton-Raphson method. But as you can see here, yes, this is the code. This is the full code, which is why I really do like the Newton-Raphson method, because look how many lines from the beginning to the end. There's 6 lines of code, 6 to 7 lines of code, however you want to think about it. So it's super easy. The tricky part, so let's go over our inputs and whatnot. So it's going to spit out our xi, the number of iterations. So remember, open methods, xi is going to be equal to our root. We call the Newton-Raphson method. We put in our initial guess, xi here, and then we put in our function f, and then we need to have another function that is called f prime. So we need to be able to take our derivative and put it into its own function. Now remember, f prime is another function, so we have to call f prime using the at symbol. We initialize our tolerance. We initialize our iteration number. We already have xi, so we can just plug that right into our f. If f, forgot one thing, forgot the absolute value. So it's got to be the absolute value, because if it's a negative value and I don't have that, then it'll just break the code. It'll be, if it's less than 0, then it'll say we converge, which is not true. So yes, if the absolute value of f of xi is greater than or equal to, I guess you can say, or just greater than our tolerance, we bring up our iterations. I did a little bit of a shortcut. So I did xi is going to be equal to xi minus this big old thing here, which is our function evaluated at xi divided by f prime at xi. It updates our xi and then x. So it's very simple. What I also could have done instead is I could have said dx is equal to negative f at xi divided by fp at xi. And then I could have done x is equal to, or sorry, xi is equal to x. Sorry, xi is equal to xi plus dx. I also could have done that. That works as well. I just like putting in a one-line code. It looks nicer when it's just like 6 lines. Down here, this bottom text, well, a text there, that is the pseudocode kind of thing for the multivariable Newton-Raphson method. So this is kind of the form that I would do if I was doing a multivariate Newton-Raphson. I would first initialize all of my functions. You can even have this as one of your input variables to your code. You're also going to have to do the same thing for the prime. So you're going to have to do f1p, f2p, f3p, and so on. You're going to have to have those functions already made, an array of functions and an array of f primes or derivatives. From there, you're going to initialize your x matrix to be 0. So you want to have an initial guess for each x or each delta x. I initialize it to be zeros. That's completely fine. Yes, yes, yes. Or yes, so sorry about that. Like I was saying, we're going to initialize our x vector. These are our roots, so our actual roots, to be zeros. This is fine because we're going to end up evaluating our f primes and our f's, our functions and our function derivatives at 0 to begin with. So that's okay. It all checks out. As long as you're not going to get a line of zeros, then you might want to have a second initial guess. Like if all of my functions rely on x being satisfied or x and y being satisfied, and I end up having a matrix that has a wall of zeros like that, then that's no good. So maybe instead of doing zeros, better notation would be ones. That's better. So sorry about that. I like that better. X is going to be ones of length f in one column. So just one big vector of x's that are ones. And then we're going to start a while loop. So while the absolute value of the norm of our functions when we plug in x. So we're taking the norm of this because we want all of them to be equal to 0. And remember, our norm is the kind of length of that vector. So if that length of the vector is 0, we know all the functions evaluated at x are 0, and we're good. If that's less than our tolerance, then we can stop. Yes. Sorry about that. From here, we hop into that while loop. I made a function here called make jack. So this is going to make the Jacobian matrix that we had before. And it's also going to make that B matrix, which is the negative function values on the right-hand side. So it'll spit out J and B being your Jacobian and its right-hand side. From there, you're going to make a dx vector, which is the Jacobian / to solve the matrix B. From there, we update our x values by doing x is equal to x plus dx. Dx being the step size and x obviously starting at being those ones. You might want to make a better initial guess for the x matrix depending on the reason you're making a code for the function of the function. But yes, hopefully that makes sense. The multivariate Newton-Raphson and the Newton-Raphson method. Let's get on to the last part of this review, which is going to be regression. Now, finally, here we're going to go to our last portion that's going to be on this midterm, which is regression. And this is, it can be hard, but if you really understand it, it's not that bad. So I'm going to try to explain it in depth so we can all understand it to a good amount. Basically, what regression is it's an optimization problem. Regression is an optimization problem. We are trying to optimize the error between our line segment that we were going to fit to our points, our data set, the error between that and our actual data set points. So we're going to start with simple linear regression, and then we're going to make our way through to our basis functions, which it's not that much different. If we were to be given a data set that kind of looks like this, I'd say, hey, that kind of looks like a line. I would draw my line through. I'd probably draw it like this. Now, the goal is to make these lines here that I'm about to draw as little as possible when we draw our line. These lines are the errors between my model that I drew and my actual points. If I had one point that's up here, well, look at that. That is a huge error. But for the most part, these errors are pretty small. So in order to minimize this error, we have to find a model that will allow us to find a minimum. We know a minimum is when dy dx, or the derivative of whatever we're trying to solve for, is equal to 0. So if we define what our error is, so our error, EI, our error at each point, is equal to y hat, which is going to be our model, minus yi, y of each point, or wherever each point is. And in this case, y hat is linear. Y hat is always going to be linear in the parameters. I like to call them weights, and I like to use the notation W. So what does a line segment look like? Well, we just mentioned it time and time again. It's y is equal to mx plus b. We're going to have b be called W0. Weights, whatever. It's going to be multiplied by the function 1. 1 is a function of x. Why not? It just doesn't have x in it. It doesn't change when x changes. Plus W1 multiplied by x. X of each point. Again, y hat W0 plus W1 x. So if we write our error is equal to W0 plus W1 xi, all of that, minus yi. Now, if we take the derivative of this, we get a constant. We don't have a minimum to this. Okay, that's all right. If we try to take the absolute value instead, well, we just come across another problem. Our error function kind of looks like that. We can't take a derivative. So what we'll do is we'll try to minimize the sum, all of the errors squared. I'm sorry, we should have put sum of all the errors. Sum of all the errors squared. What does this give us? It gives us a nice convex function. Oops, that looks like a parabola. just like that. And if we minimize that, we can actually find a minimum. So we have to minimize what we call our SSE, sum of squared errors. And that's equal to the sum A0 plus A1 xi minus yi all squared. In order to minimize this, we are never going to take the derivative of our x or our y. We're never going to take the derivatives of our function because we know those. We're given a set of data. And obviously in data sets, we're giving sets of points. We have the y of all of our points. We have the x of all of our points. So why would I take the derivative of points, right? It doesn't really make sense. But wouldn't it be easy if I just took the derivatives of our parameters? Sorry, I'm falling out of notation. W0 and W1. I just take those derivatives. That's not bad. So let's try that. To minimize the sum of square errors, I can take the derivative with respect to A0 and equate that to 0. I get 2 multiply the sum of W0 plus W1 xi minus yi. I'll do the same for my other parameter. Why do I keep putting 8s? I apologize. W1. That's equal to 0 to 2 multiplied by the sum W0 times xi plus W1 xi squared minus yi xi. That is because, well, I can't take the derivative with respect to W1 there. I can't take it from there. But if I take the derivative of this, I end up just getting xi, which gets multiplied into my function. So my 2's can just get divided by 0. If I sum a constant, so if I ever have the sum of 1, or the sum of 2, or in our case, the sum of W0, we take that constant out of the sum. We call our sum n. Because if we're just summing over 1, we're just taking the amount of values that we have. We're just adding 1 every single time. Sum of W0 is just W0 multiplied by n. And do we know W0 or W1? No, we're trying to find those to fit our model. So what do? We have 2 equations, 2 unknowns. We have a bunch of knowns. Let's throw it into a matrix. MATLAB can solve those pretty easily. So we get n, and then we get W1. So this is going to be 0, 1. W1 is multiplied by xi in the first equation here. Then we get sum W0 is then xi. W1 is then multiplied by xi squared. Cool. W0, W1. That is going to be equal to sum of yi and sum yi xi. And that's a regression function. That is linear regression. Cool. Now, let's say we don't want to do just arbitrary linear regression. Let's say we want to do some polynomial regression there. We got to minimize our sum of squares. And what we can do is, when I code, I like thinking generally. I think generally, what am I doing here? Well, I'm always going to have n here because I'm always going to have an intercept. This is just my W1 function. This is also the function that's multiplied by W1, and this right here is going to be the function that's multiplied by W1 squared. And I have a 2 by 2 matrix. And I have a 2 by 2 matrix, and I have one of my parameters being multiplied by a function of x. So in the end, I'm going to get 2 multiplied by n being my biggest value of my parameters, being 1. So in our case, it's just 2. Generally, in general, it'll look like this. Yeah, number n, and then for the first row, it is going to be multiplied by all of our functions. In our case, our functions are always going to be xi, because it's polynomial, so we're going to have an xi. And then if it's a quadratic function, we're also going to have something multiplied by xi squared. We're going to go all the way until we get xi to the power of n. From there, my whole first column is also just going to be our functions. If we have n as our intercept, if we have a w0, which we'll have a w0, we'll have a w1, all the way to wn, you know our w0 is multiplied by 1. The first derivative, which is always going to be my first column is my first derivative, no matter what. My first derivative is just going to be 1 multiplied by every function. Sum of xi, sum of xi squared, sum xi to the n. What I like to do whenever I do any kind of a regression, I like to take my rows and I like to duplicate it. I like to start from the beginning and I like duplicating it all the way down. I duplicate it all the way down there. From there, what I like to do is I like to take whatever's here, in this case, we'll start for xi, and I like to multiply that by every single other function in that row. So we get xi squared, xi cubed, and then we get xin plus 1. Let's do the same thing for this row. We'll multiply everything by xi squared. We get xi3, xi4, xin plus 2. When we get to the very end, we end up getting all of that stuff. At the very end, we get x to the n plus n. Wouldn't you know, also the sum of x to the 2n. The right side is always going to be the same too. Assuming we have one function that is just 1, we're going to start off with the sum of yi. Then for every subsequent row, the mx, all the way until we get yi times xi to the power of n. Now it's important to remember, the higher order we do, the more prone to overfitting. The more prone to overfitting our model is. Now, what overfitting is when our line segment that we're drawing goes through all of our points. So let's say our points look a little something like this. Overfitting would be if I drew a line through all of my points. So in this case, I'd have 1, 2, 3, 4, 5, like a sixth or seventh order polynomial. That's no good because they're unpredictable. We don't know what they're going to do outside of our points. We have points here. We have points there which we forced our polynomial to fit those points. But do we know what's going to happen when we get to our no point region? Well, no. And with seventh order polynomials are unpredictable. It could end up looking like this. It could end up looking like that. It could end up looking like this. We don't know. Right? So this is why we always keep it to a simple polynomial number. We still want some errors in our data set. This here, this has no errors. Right? If we're to take like an R squared value or something, it's going to be 0. Because can I measure a distance from our point and the line? No, it's 0. There's no errors. And that's not good for a model because we want to know there's a little bit of error. We want to know, yeah, our model's pretty good, but obviously these points are random. I can't get a perfectly fit model. So that's why it's important not to overfit. Now, let's say, for example, we don't have just any old function of x. Let's say we want to regress sine x, cosine x, ln of x, something like that. Can we do that? Well, we're not going to be able to fit parameters inside of those functions, right? But can we find what those functions are going to be multiplied by? The coefficient? Sure we can. We can do the same thing, the sum of square errors. Let's say our model looks something like this. I'm going to use, still going to use W's. Sure, I can do that. The derivatives are still just going to be our functions. We have 3 functions here. F0 being 1, F1 being sine x, and F2 being ln x. We have those 3 functions. Now, if we were to make our polynomial, our non-polynomial, our basis function matrix, it's pretty simple. Let's do what we did before. Our first top left corner is going to be n because we're trying to sum over W0, and that's just going to be cool. Now, remember what we said before. We got to sum up over our functions. We're multiplying all of our functions by 1. So we get the sum of F1 and the sum of F2. Same thing here. Sum of F1 and the sum of F2. We would go all the way till we get the sum of Fn. Sum Fn. Now, let's duplicate all the way down to the end. And let's see what we end up getting. We get the first one, F1, sum of F1, sum of F1 squared. Then we get the sum of F2 multiplied by F1, sum of Fn multiplied that by F1. We go to the very end, the very last row, repeating sum of F1 times the sum of Fn, sum of F2 times the sum of Fn, sum of Fn, sum of Fn, sum of Fn squared. And what's cool, and what you'll notice is that for all even basis functions, but I'm going to show you on the general function. Actually, I'll show you on the basis function too. We'll do this. Do one squared. Let's see. Cool. We take our diagonal here. It's symmetrical. Yeah. F1 and F1. Then we got F1, F2. That should be in there too. Oopsies. We got our diagonal all the way over here, F2, F2. We got F2, Fn, F2, Fn. Is that it's symmetrical along the diagonal, which means as long as we can get this upper triangle here, we just copy it down to our lower triangle. Pretty easy. We multiply this by our weights. And that equals, just like before, y, and then F1, all the way down, Fn times 1. Now, usually F0 is 1, but is F0 always 1? No. So generally, this would be F0. This would be F1, F0, and so on. Most of the time, you can rely on that being 1. All right. We got one last concept to go over. We'll go into MATLAB. We'll do a regression for just random regression model, general regression, and then you'll be finished. So we got a multivariate basis function. Now this, trust me, this isn't that bad because multivariate basis functions are actually pretty easy. Regular basis functions, we have to sum over one variable. And our functions are of one variable. This time, we'll do this. This time it'll be the exact same thing. Our f's can stay, but these functions are functions of two variables for the most part, x and y. Before we move on, functions of x and y can look like this, or they can look like this. They can be functions of x and y, they can be functions of just x, functions of just y, or just constants. It's still a function, it just doesn't change when one of the other variables change. So what do? Well, instead of this, I'm going to write the n for how many, will be nx times n y, because how many sums do we have this time? We have two sums. Add a sum everywhere. And so everywhere gets another sum. Each of these sums correspond to a different variable. One is the sum over x, and the other is the sum over y. Let's hop into MATLAB. We'll code the univariate basis function or general regression, and then we'll do a multivariate. All right, everyone, this is the last coding demo of this review session. We're going to be going over regression and multivariate regression. So what this function is going to output is going to output a vector of weights. So all of our weights, all of our parameters is going to give us. It's going to be equal to our regression function. We're going to have to feed it in x and y. So we're going to have to feed in our x vector and our y vector, which are our points, which we know. Remember, we know our points. We just don't know the weights. From here, I'm going to initialize a few functions that our matrix relies on. You could also add these in as an array at the beginning. I like just making it here. From here, notice what I do. That's a function, or sorry, that's an array of a bunch of functions. So I got to use the curly brackets here. I can't use the squares. I have to use the curly one. That's very important. So curly brackets, array of all my functions. I then initialize my A matrix being the zeros, length F. So that'll make a square matrix. In this case, 3 by 3, because we have 3 functions and 3 weights. B is going to be the length of F, 1, because it's a vector. All right, from here, we're going to do a for loop. So remember what this for loop is going to do is it's going to propagate the upper triangular matrix, the upper triangle of the matrix. And we're going to do a little bit of a trick to also propagate the lower triangle. Remember, this is important because our regression matrix is always going to be symmetrical. So we have 4 I is equal to 1 to the length of F. So this is going to do every single row. From here, since our B vector is only getting updated once every row, remember, it's not going to get updated when we go over our columns. Because let's say, for example, for the first row, we're going to iterate over all of the columns. If we update our B value every single time it goes over the columns, then we're going to get a huge B value, not going to be accurate, and we're done. We're toast. So that's why we do it only once every row. Now we're iterating over the columns. So for J is equal to I, we're going to start at I, because remember, we only want to propagate that upper triangle. So when we go down one row, we also hop over one column. And we go all the way over to the very end, the length of F. And then simply Aij, so the row that we're at and its column is equal to the sum of all of these values. F at I at value greater than X times the function that is in the J index at X. So what this is doing is it's calling remember what we said before, whatever row we're on, we're multiplying all of our other functions by that at X. And then in our column is going to be changing every time that this iterates. This iterates here. And what's very important is you notice every time I'm kind of multiplying something, I'm doing this little dot operator. It's important because we want to do matrix index-wise multiplication. So if we don't add this dot, then what MATLAB's going to do is it's going to think we want to multiply matrices, which is incorrect. We want to just do vector or index-wise multiplication. So index 1 multiplied by index 1, 2 by 2, and so on as we go down those vectors. We don't want to try to do matrix multiplication. So this is why we add that dot. It's going to do vector or array-wise, index-wise, sorry. From there, we made AJI equal to AIJ, remember, because it's symmetrical. So 2, 1, or 1, 2 will be equal to 2, 1, and so on and so forth. We end, and then we create our weights vector by just solving that system using the / command. That's normal regression. We go over to multivariate regression, and it looks a little bit longer, but essentially is doing the exact same thing. This time we have to put in an x vector, a y vector, and a z vector. Now the x and y vectors are values that are going to be used on the left-hand side, because remember, we have to do 2 sums now. And our z vector is the one on the right-hand side. Z is a function of x and y. From here, we're initializing our variables, or our functions rather. And remember, we can have a function of x and y. We can have a function of x, a function of y, and a function of neither. From there, again, we're initializing our a's and our b's, nothing too fancy. From here, so what's interesting about this is you can do this two different ways. I chose to do this a way where we first propagate our matrix and then we propagate our vector. There's also another way to only use one big for loop. That would be a good exercise for you to do on your own. But what it does is obviously, this is also very important. We're only here for multivariate. So the way I like to do multivariate regression is I like to use these for loops. And what it basically does is it does our summations either time. So every single time we hop into a new column, we have to put our sum to 0. Okay? So that's very important. Every time we move our j, we got to make our sum 0. From here, we're going to do another for loop for k from 1 to the length of y. What this does is it starts our summation over the y value. Remember, we had the sum of y, sum of x, then our functions. It starts the summation over y. We make our variable y equal to y at the current index, and then we go to our x summation, which is going to be changing quicker. So we have our summation of y, summation of x, and then our functions. Our y will stay the same as x iterates through all the x's. And then our y will go up 1. And then our x's will go again, and then our y will go up 1. All while summing these values. So we make our x equal to x at q. And you don't have to do these dots because we're not doing index-wise operations anymore. We're actually just making our y is equal to whatever indice it is in the y or x vector. From there, we update our sum. Our sum is equal to the previous sum plus the same thing at the I at the current x and y, fj from the function right up here, evaluated at our current x and y. Now, this is important. If k is equal to the length of y, so if k is done iterating, then we're going to update our a values. So if k is on the very last iteration, it does all its sums. We update our a values to be, so aij is s, ji is s, and then what it's going to do is it's going to pop back up to 4, j is equal to I plus 1, the next j value. Finally, what we're going to be doing is we're doing our b vector. So for I is equal 1 to length f, SB is equal to 0. It's the exact same thing, but now notice we don't have that second J for loop. This is because we only want to update our B vector, as I said before, once per row. And it just gets a little bit complicated when we do the first loop. You can do it. I challenge you guys to figure that out. I do have a code that does that as well, so you can just contact me if you want to see if you're correct, or just try it out yourself. We do have a practice problem. So again, we go through all of our y's, we go through all of our x's, make y that index, we make x that index, and then we update our SB value, the sum of b, to be f at I, whatever I is, whatever row we're on, multiply by z, the z value. Since our z value is the same length as our x and as our y, we can do z at the q index. There, the same index as our x. From there, if k is equal to the length of y, then we update our b matrix. And we solve for w. That's it. Now, I know this is a lot to take in. It's a lot. You can pause the video. You can copy down this code, convince yourself that it works. Go ahead and practice. Other than that, thank you for watching. Hopefully you learned something today. And good luck on those midterms. Good luck on those exams. And I'll see you in the next video.